All right, so this first screen is just basically summarizing everything that we did in sections 4.1 and 4.2, and it should help you to get through the homeworks. All right, so anytime we're dealing with an exponential formula, we have the exact same formula. Now this is if it's a percent increase, it doesn't matter. If it's a constant multiple of any kind between a previous term and the next term, and that constant multiple is constant for every single increase in t, then we have an exponential function. All right, so I just want to label these parts for you to make sure you know what we're doing. We have our function name, which is n in this case. Our function name is n. Sorry, let me get my correct pen out. This is my function name. All right, this is typically what we're looking for, some amount of it would be from the context, but this is some amount that we're tracking, right? It's a function of t. T is the input variable, and it shows up in two places. It shows up in the function notation at the front, and that same t shows up in the exponent of the growth rate or decay rate. Right? P is always the initial value. So if you are told that some amount is present when an experiment starts or when a population is being modeled, when they first move into a certain area of forest or something like this. This would be your initial amount. You can usually solve for this. I think in class I showed you how to solve for n of 0, right? But usually they tell you directly what it is. They give you some initial value. They reference initial or at the beginning or when the experiment started, words like that, they're talking about P. They're talking about the initial value. A is the growth rate. It's this constant multiple. It can be greater than 1. It can be less than 1, but greater than 0, right? So if it's a fraction or a decimal less than 1, you have a decay rate. If the number is, this would be something like 0.944, which is a number that you'll be seeing later, right? That constant multiple is a decimal like this, it's less than 1, then you have a decay rate. If you have a rate that is greater than 1, your constant multiple is greater than 1, that could be something like 1.08, which again is a number that you're going to see in the next homework problems, then you are actually having a growth rate, right? So if you're given a percent, then you have to be careful, right? You have to take R and convert it in. R is the percent. You need to take R and turn that into a decimal before beginning. So if you have a percentage growth of 5% every year, before you start making your model, you need to convert 5% into a decimal. And 5% is 5 out of 100. So that would be like a nickel or 0.05, different ways to think about it. All right, so then you could calculate A. The formula was given in class, but it's 1 plus R if you have a growth rate. So in this case, it'd be 1 plus 0.05. Oops, sorry. 0.05. So A in this case would be 1.05. All right, so make sure if you have a percent, you convert R into a decimal before beginning. You can see it's going to make a really big difference. If I did not convert this into a decimal, I would be adding 1 to 5. 6 is completely different than 1.05, and the resulting function would be absolutely wrong. It would be growing way too fast. All right, so just make sure that you pay attention to your R values. All right, so read the questions before you watch the solution. All right, it's the best way is to give yourself a chance to make a mistake and then see how it can be corrected. If you have any questions after watching the video, feel free to send me an email. Okay, good luck. All right, so we have a very, very loose context here. An amount A is initially 13. To find the next year's amount, we multiply this year's amount by 3. Without even telling you any interesting context or crazy information, they told you that you have an initial value, the initial amount, initial value is 13, and then they tell you that the constant multiplier is 3. Since that value is greater than 1, A is a growth rate, and a equals 3. And that little a that I'm referring to is from the general form of the exponential function, which is a equals p a raised to the t power, all right, where the capital A is this amount that they're referring to. This is the amount that they're referring to. It's some sort of function name. P is always the initial value of the amount, so the initial amount. And A is some sort of growth or decay rate, right? So when A is greater than 1, we have a growth rate. And when A is less than 1 but greater than 0, we have a decay rate, all right? So what we need to do is just fill in the pieces that we were given, all right? We have A equals, the initial amount is 13. I'm substituting 13 in for P. We're multiplying that by the growth rate in this case, which is 3. So the final answer here, make sure you enter it in very carefully, is 13 times 3 to the t. A lot of common errors would be that you think you can type in 13 times 3 to the t. This is not right. Only the 3 is being raised to the t power, all right? So keep that in mind, those little details when you're going through the rest of the questions as well. All right, so as always, make sure you understand the context of the problem before you get started watching the solution, right? You should have tried the question at least once before you're listening to the solution. So we have a violin, and in order to make notes higher on a violin, you have to make the string shorter, and that shorter string gives you a higher note. And the same thing happens with our vocal cords. When we sing, when we talk, and we try to change however high and low we need to talk, okay? So in order to create, in part A, an exponential function, right, that gives L as a function of n, right, what we need to do is use our general exponential model, which is initial value times growth or decay rate raised to the t power. Or in this case, and let me be pretty good about my variables here, we're actually going to use n as our input variable. So I have L equals P times A raised to the n power. That's my general exponential form. Hopefully you can see that this is an exponential form, even if I don't tell you directly in the question. The way you can figure that out is with this sentence here. The current length is multiplied by 0.944. That means every time we need to make the next higher note, we multiply the current length by 0.944. That constant multiple is what makes this an exponential function. So let's go ahead and try to come up with what our formula should be. I'm going to copy that general form again down here. L equals PA to the n. Right. Looks like L pan. So what we can do is try to figure out the different pieces. I need to know what is P and what is A here, my growth rate. So just from the context, a lot of this is given. We should have L is equal to the initial length of the string, and it says the length of an unstopped string is 32 centimeters. 32 centimeters is the length of the string without trying to go to any higher notes. This is the initial length. Therefore, it is the P value. The A value is that constant multiple. The constant multiple in this case is 0.944, and it's all being raised to the n power. All right. So all of that just came from context. Most of these you will be able to figure out the formula just by reading the context. So this is part A for my numbers, and for part B, what are we trying to do? One of the unstopped strings makes an A note. To what length must the string be stopped in order to make C sharp, which is 4 notes higher? Well, without reading the context, you might not realize that n represents the number of notes higher on the string we need to go, okay, in order to make this new note. So to go from an A all the way up to a C sharp, we have to go up 4 notes. That's N equals 4. So what we can do now is figure out the length of the string using our formula. We're trying to determine what is L of 4 here, right? Our input variable is N. So L of 4 equals 32 centimeters times 0.944 raised to the 4th power. And you can use your calculator to figure this out. Either you can let y1 equal your whole formula for L, which would be 32 times 0.944 raised to the x power in your calculator. Or you can just, in the main calculation screen, type in 32 times 0.944 raised to the 4th power. Now, if you had to do a lot of questions with this particular formula, I would just type it in as a function so that I could use the table. But if you're just doing one calculation, it might be too much work for you to go type that in. So sometimes just typing in exactly what you're looking for can give you the correct answer. The hint here is to make sure you round to 2 decimal places, only 2 decimal places, okay? So round properly on that one. All right, so go ahead and pause the video, make sure you understand what's going on in this question before I get started. When I first read this problem, I wasn't sure that you would be able to tell if this was an exponential model or not. In part A, it tells you find a formula for an exponential function, but if it didn't tell you that, would you know that this was an exponential function that needed to be used to model this situation? Now, I just wanted to specify here how I know that this was going to be an exponential model. Okay, so I'm reading through. A woman who has recovered from a serious illness begins a diet regimen. She needs to gain weight. She currently weighs 102 pounds, right? So there's a little bit of information given here, but that doesn't tell me that this is an exponential model. The next sentence is what confirms that this is an exponential model. She hopes to multiply her weight by 1.08 each week. This is a constant multiple. Okay, constant multiple. I'm not adding to the weight every week. I'm multiplying my weight by a certain value every single week. So find a formula for an exponential function, let's see, part A, that gives the woman's weight W in pounds after T weeks on the regimen. So straight away, I can just jump to my general form, which is going to be W, my function name, is equal to the initial weight times the growth factor raised to the T power. This is our just general form of an exponential function. This works for exponential growth. It works for exponential decay. In this case, we have an exponential growth problem, which tells me A will be greater than 1. So let's go ahead and try to use some of the given information to figure out what P and A need to be in order to make this model work. W is the name of the function. That's not changing here, all right? I'm not looking for that. I'm looking for a formula, W equals, and you can see that right up in the part A question answer spot, right? P always represents the initial value. When we start this diet, we weigh 102 pounds. That's my P value. The constant multiple from the last sentence here, the constant multiple that we're hoping to raise our weight by every week is 1.08, and that just pops directly into the function, right? So for part A, with my numbers, this is the formula that I'll be using. In part B, it says, how long will it be before she reaches her normal weight of 125 pounds? So she needs to gain 23 pounds in order to get back to this normal weight, her normal weight. Right? We can use our formula here and remember that W represents weight. So if you have a known weight, you can substitute that value in wherever you see a W. All right, so on the left-hand side where I have a W in my formula, instead I'm going to write the normal weight I'm trying to reach, which is 125. So 125 pounds equals 102 times 1.08, just following our formula here, to the t. The only method that you have at this point that I've taught in this class to solve nonlinear equations is the crossing graphs method. Crossing graphs method. Now, I've said this so many times, so hopefully this feels very familiar. I'm just going to get you started on this, but you have to finish this process, all right? I've got my left-hand side of the equation is y1, and I've got the right-hand side of my equation is y2, which is 102 times 108 raised to the power of t. And actually, I need to erase that t, right? Because we're not using t when we use the calculator. When we answer the question, yes, we will use t, but when we use the calculator, we use y and x here. So I've corrected that for you. Now you're gonna have to figure out how to adjust your window. You need to change your x's, you need to change your y's in order to see the intersection of these two lines. So if, for instance, all you see is something like this on your graph, or maybe you don't even see anything at all, you definitely cannot see the intersection point on the graph I've just drawn. That's very clear. You need to probably increase your x's and increase your y's. I would say your y values need to go all the way up to 130 because I know one of my y values is going to be 125. Okay, so here's my 125. And you're going to have to determine how far do my x's need to go out, how long, how many weeks does she need to spend on this regimen in order for the exponential graph on the right-hand side to cross the constant graph of 125, right? And you're going to be using your crossing graphs method, which is second trace option 5 for intersect. Trace option 5 is intersect, and then you'll follow the prompts there. All right, so get some practice with this, and the x-coordinate of the intersection is going to be the number of weeks that she needs to spend on that regimen. Okay, so that will be your answer for this problem. All right, so in this science-based question, we are discussing a radioactive substance that I'm just going to call iodine, but it's called iodine 131. Okay. The amount of this substance has been measured a couple of times in this problem. Okay, they were able to detect a certain amount of the iodine at one point, and then 8 days later, they saw that only half of that original amount was still in existence. Because we're talking about a population, we're talking about a half-life of a radioactive substance, we know that we can use the exponential model. So I wrote n equals p times a to the t because that is our general formula for an exponential model. I labeled what all of the parts mean as far n is the amount of iodine 131 at any time. It depends on time, the number of days that have passed. Okay. We've got p, which is the initial amount present in this area, thousands of miles away from Japan. We have a decay factor. It's the constant multiple that the initial amount gets multiplied by t number of times, which is, of course, the number of days. It's our input variable. So we're going to try to use some of the information that was given to us in the context of the problem to figure out what is the daily decay factor for this substance. You can see here that I've written the same formula, but with some of the information that they gave us in the context of the problem. P is still the amount that we initially have of this iodine substance, so it's still the initial amount. Now, all we know is that 8 days after the initial measurement of the iodine, we have half of the initial amount of iodine left. Okay, that's the idea of a half-life. It means half of the initial amount is gone. It has decayed away. So how this comes into play in our formula is I've substituted in 1/2 p for n because 1/2 of the initial value is the amount that I have left. And I've substituted in here 8 where t is in my formula because it took 8 days to get half of the initial substance decayed away. Now, because we only have the crossing graphs method, if we're trying to solve nonlinear equations, we have to get this down to where we only have one variable. Right? We need to get one variable in this equation. And what I'm going to do now is show you how you can do that for this problem. So we have 1/2 p, that's like 0.5 p, equals p times a to the 8. Now, the variable that I want left in the equation is a, because I'm looking for the decay factor. That's the whole point of this problem, is to find that decay factor. So somehow I need to do some algebraic manipulation, some symbolic movement to get rid of this p. So I have p times a to the 8th. I'm trying to get that a to be the only variable left. So what I'm going to do now is divide both sides of this equation by p. This is something that we have done before. We've done division like this. Now, whenever you have some value or some quantity that appears in both the numerator and the denominator an equal number of times, they cancel each other out. This is p divided by p equals 1. And on the right-hand side of the equation, the same thing happens. I've got p divided by p gives 1. So all I'm left with is 1/2 times 1, or just 1/2, equals 1 times a to the 8th power. So look at this. I'm left with 1/2 equals a to the 8th. Well, our calculator doesn't recognize a as a variable. So to use the calculator, that's a little sloppy, but calculator, what you're going to do is you're going to let y1 equal 1/2 or 0.5, and you're going to let y2 equal x to the 8th. Okay? So you're going to have some sort of graph that you can go look at. One of the values will be 1/2. That's one of our functions that you're going to see on your graph. The other graph is going to look something like this. It's going to go whoop, okay? And what you need to do is find that intersection point. The x coordinate of that intersection point will be your decay rate. It will be your answer here. So I'm going to let you finish this problem on your own.